Hi, everybody. Welcome back to my lecture series on sustainability issues in energy. We're going to continue today talking about hydrogen. In the previous lecture, we learned about how you can make hydrogen, where you can get hydrogen from. And now we're going to talk about how you can transport that to end users. So the question today is, so you've made your hydrogen, you've gotten your hydrogen from somewhere, and now what are you going to do? So here's this figure from the IEA, and you can see that they're listing a number of different techniques for collecting the hydrogen and then either transmission or distribution to the end user. And each one of these methods here is color coded by the form of hydrogen that you can use for that particular technique. So, for pipeline, for example, you can use hydrogen gas, but you can also transport hydrogen in the form of ammonia through pipelines or trucks or boats. And so we'll talk about in this lecture and then the next one that I'll post later, we'll talk about the different methods for getting those different forms of hydrogen and then how we move them around. Okay. So overall, you can see that there's a number of different ways of moving the hydrogen around that some of them have, well, I mean, like anything, they've all got issues, right? So there are good points and there are drawbacks. A lot of them involve, various conversion and reconversion steps. That's particularly true when you're transporting the hydrogen in a form that is not the form that the end users need. So, for example, you can see that most of the end users are demanding hydrogen gas or potentially ammonia in some cases. And so if you're transporting your hydrogen either in a liquefied form or with a liquid organic hydrogen carrier, there has to be a reconversion back to your useful form of hydrogen. So that's one thing we have to think about. There's also, the need for storage and other types of chemical conversion along the way. So that's something else you need to consider. Okay, so overall, the issue with storing and transporting hydrogen is that hydrogen has a lot of energy per unit mass, but it is much less dense than methane, which is the principal component in natural gas. And so that means that per unit volume, it has a very low energy density. And this is important because a lot of the way that we talk about moving around natural gas, we're specifying volumes. Okay, so billions of standard cubic feet or billions of cubic meters, that sort of thing. That's all a volumetric measurement. And so hydrogen kind of loses when we talk volumetrically because it has such a low density. A good way of, or maybe a better way of thinking about this is if you compare the rate of energy transport or energy storage per unit mass or per unit volume, that makes it a little easier to compare because really what we're doing whenever we're moving hydrogen around is that we're moving energy around because hydrogen, we're using it for energy. So here are some comparisons of mass-based energy density and volumetric energy density between hydrogen at different conditions and then natural gas. So if we're looking at normal temperature and pressure, hydrogen has a mass energy density of 142 megajoules per kilogram. That's almost 3 times the mass energy density of methane at the same conditions, and higher as well than gasoline. But like I was saying, look at how the bulk density differs. So it's almost a factor of 10 lower than methane at normal temperature and pressure. And so because of that, when you convert this to a volumetric energy density, hydrogen has about 1/3 the volumetric energy density compared to methane at normal temperature and pressure. Now, and that deficit cuts down to about a half if you compare liquid hydrogen to liquefied natural gas. But there are some issues with liquefied hydrogen that we'll talk about in the next lecture. You can kind of get an idea for that just by looking at the difference in temperature between LNG and liquid hydrogen. But anyway, the point here is that hydrogen has a low density, so per unit volume, it has much less energy than natural gas. Here's yet another plot showing that. So if we look down here at the x-axis, they're calling it gravimetric energy density, but again, that's mass-based per unit mass. You can see that hydrogen is highest, but then on the y-axis, these are volumetric energy densities, and you can see that even liquefied hydrogen is substantially lower than some of the more conventional hydrocarbons that are used. Diesel fuel has a very high volumetric energy density, so just something to consider there. Okay, so let's think about trying to move as much energy around in a pipeline with hydrogen as we have with natural gas. So as an example, let's look at the Permian Highway pipeline, which is the green one here in this map. It goes from the Waha hub out here in West Texas in the Permian down here towards the Katy area, where there's a number of distribution pipelines to take it to either to end users or to LNG facilities. So the stated capacity of the Permian Highway pipeline is 2.1 BCF per day. So that's about 59 million cubic meters. So that, again, that's a volumetric estimate. So what flow rate of hydrogen would be necessary to get the same energy flux through the Permian Highway pipeline? Okay, so let's just do a really simple back of the envelope calculation. We'll just consider the properties of natural gas versus hydrogen at normal temperature and pressure. Yes, I know that the gas is compressed when it goes through the pipeline, so that's going to increase the volumetric energy density, but let's just keep this simple and not deal with equations of state right now. Okay, so natural gas has 33 megajoules per cubic meter at normal temperature and pressure. So if we move that through the Permian Highway pipeline at its maximum capacity, we're moving about 1.9 gigajoules per day. Okay, so that's our benchmark. Now, because hydrogen has a lower volumetric energy density at normal temperature and pressure, to get that 1.9 gigajoules per day, we would have to increase the flow rate to 160 million cubic meters per day. So it's about 3 times higher than the natural gas flow rate. And that should be fairly obvious because there's roughly a 3x difference in the volumetric energy densities. So you'd have to design, go back and redesign the compressors and the size of the pipeline and everything to be able to handle that higher flow rate. You could also do that by increasing the operating pressure by roughly 3 times, assuming more or less ideal gas behavior. This one's tricky because compression is always the most energy intensive component of moving gas around. It requires a lot of energy, it's inefficient. And so, you don't want to just be relying on compressors to get this through because you're going to end up wasting a lot of energy. So there's different design considerations that you have to take into account if you're thinking about simply repurposing pipelines. Okay, so let's focus in on the pipeline issue a little bit more for the transmission and distribution. So this is a map of natural gas pipelines in the US. We've got about 3 million miles as of 2021. And so, if you're thinking about, okay, let's assume that, we can just use those for transporting hydrogen. What's the problem with that? You can see that there's already a lot of existing infrastructure. So you got to think about what pipelines are made out of. So here's a nice pie chart showing the types of materials that pipelines are made out of. You can see about a little more than half are made out of plastic. And then the other half are mainly some type of steel or iron. There's some high rollers, I guess, using copper pipes. But for most of these, this is going to be some kind of a steel. Okay. So what's the issue with that? Okay. So steel is a mixture of iron, carbon, and then a bunch of other stuff that is either added to give particular properties to the steel or simply impurities. And here's a long list which you can go through at your leisure if you're interested. But boron, chromium, molybdenum, those are some of the more important ones, particularly in stainless steel. The American Petroleum Institute specifies the composition of pipeline steel, and they specify it in terms of carbon, silicon, manganese, phosphorus, sulfur, vanadium, niobium, and titanium. And so, that's not all of the additives that are in this list, but at least the API is specifying those to be, standard API steel. Okay. Hydrogen is a very reactive molecule, and particularly it likes to do bad things to steel. And so this is a kind of a busy table, but the important things here are looking at the different types of hydrogen damage. So there's embrittlement, stress cracking, loss of ductility, blistering, shattering, flaking, microperforation, and even metal hydride formation. So these different issues with steel arise under different conditions, so different pressures, different partial pressures of hydrogen, and they all work in different ways too. So here's a non-exhaustive diagram of how some of these work. So hydrogen is a very small molecule, so it can diffuse through the atomic lattice of the steel and get into these voids where it will accumulate and eventually expand to the point where you've got these gas-filled voids that eventually can crack. It can stick to the surface inside existing defects in the surface of the steel. The individual hydrogen molecules can get in and cause something called decohesion, which is where they cause the atomic lattice to kind of break apart. And also causes dislocations in the lattice, which gives you soft spots, so a little bit of a messed up lattice there. You can form metal hydrides, so particularly with niobium, vanadium, tantalum, zirconium, throwing out my geology there, zirconium, titanium, and magnesium. These hydrides are brittle, and they can cause cracking in the steel. You've got carburization and decarburization reactions at higher temperatures. And you can even just trap the hydrogen in the steel, which tends to weaken. So these are all bad things that happen with steel pipelines. So you got to think very carefully about the material that your pipes are made out of if you want to move hydrogen through an existing pipeline. Well, okay, so you're probably saying, what about the other half of the pipelines that are made out of plastic? Okay, so maybe you don't have the same corrosion issues with plastic, but here we're looking at the atomic scale, the structure of methane over here, and then this is a hydrogen H2 molecule here. And the van der Waals radius of H2 is smaller than that of methane, so 380 picometers versus 289 picometers. This means that it can diffuse through plastic faster than methane. And so you'll end up losing some of your hydrogen over the course of the transport, even if you're using plastic pipe. So here's a plot of leak rates for a mixture of hydrogen and methane in HDPE pipe at 60 psi. In general, the hydrogen loss rate is about 6.7 times higher than the loss rate of methane, but it's still relatively small. You can see that at 100% hydrogen content, you're losing about, I don't know, what is that, 330 cubic feet per mile per year. So, it's still not zero, but it's relatively small. So maybe this is something that, you can just accept as a loss. Now, okay. Later on in a subsequent lecture, I'll talk a little bit about why we want to minimize hydrogen leaks, because it actually is not such a great thing to get into the atmosphere. But at least we're, comparatively losing less, not a whole lot of hydrogen through this diffusion issue. And so one thing you can do actually is that regardless of the type of pipeline you want to use, if you want to use existing infrastructure, it probably makes sense to try to blend hydrogen with natural gas. NREL, the National Renewable Energy Laboratory here in the US, estimates that our existing pipelines can take up to 50% hydrogen mixture without any type of upgrade. So that's pretty good. The issue then is that what you're delivering to your end users is a mixture of hydrogen and natural gas. And that can be used, you can combust that, or if you need pure hydrogen, then you would have to separate it out at the end. You can use membranes, absorption, steam methane reformers, that sort of thing. So that's something you need to think about. Here's a plot of various transmission and distribution infrastructures and then various end users and the amount of hydrogen blend that they can take without any upgrades. So I mentioned that 50% figure here. This is a IEA figure, so it's not strictly US, but they're estimating that under some circumstances, you can actually use 100% hydrogen for your distribution system. But most of this, you can see that, we have to have lower amounts of hydrogen. In Europe, a lot of their heaters and cooking appliances are certified up to 23% hydrogen. And this has somewhat of a historical basis because of the use of town gas that goes back, hundreds of years in some cases. And the town gas in a lot of parts of Europe would be some kind of mixture of natural gas and hydrogen and carbon dioxide. So you're combusting this kind of mishmash of gases to begin with. In the US, there's not a certification like that, but according to NREL, they think that American appliances could take up to 28% hydrogen. So that's one possibility, at least for combustion. But other types of existing infrastructure can't take very much hydrogen. We'll talk about the problem with gas turbines in a subsequent lecture when we're talking about electricity generation, but the way that hydrogen burns is different. The flame speed and the ignition temperature and everything are different than they are for methane. So existing gas turbines that burn natural gas don't really work for hydrogen. They have to be redesigned. So that's an example of kind of on the material and infrastructure side, what could be withstood. Now, countries have already started regulating how much hydrogen can be blended into their natural gas networks. And one thing to note is if you compare the x-axis on this plot, you can see that the percentages are much lower than they were on the previous slide. So, France has the highest permitted mix, and it's 6%. So it's not very high. In North America, utilities have identified 15% target, but we're not quite there yet. In Canada, they're allowing 5% blends, I believe. So it's not maybe what you would hope. But the thing with this is that, yes, you're still mainly using natural gas, but you're reducing the carbon intensity of the end use by mixing in a little bit of hydrogen. So that, per unit energy that you're using, you're generating less CO2. And so you're not totally decarbonizing the end uses here, but you're helping out a little bit. So this is one of those don't let the perfect be the enemy of the good scenarios, I think, at least in my opinion. So this is something that hopefully we can see more of moving forward. Okay, so pros and cons of blending. I mean, obviously, you can use existing pipeline networks with minimal modification, and you also reduce your methane leakage. But then the cons is that when you're replacing natural gas with hydrogen, you're reducing the volumetric energy content. The blended gas burns a little bit differently. It has a hotter flame. The flame is harder to see. Methane has an almost invisible flame, whereas natural gas obviously has a blue flame. So there's a big difference there. If you need pure methane or pure hydrogen for your end use, you can't take blended gas because you're going to waste a lot of energy separating it out. And there is an increased cost. It's estimated to be about an extra 30 to 40 cents per kilogram of hydrogen that you add. So there's also that to consider. But hopefully we can get some of these issues worked out, and maybe you'll start seeing more hydrogen blends in our natural gas network. Okay, so that's all for this lecture. Next time we'll do part 2 of our transportation unit. We'll talk about liquefied hydrogen transport and hydrogen carriers. So I hope you've enjoyed this lecture. Feel free to subscribe to my channel. You get alerts whenever I put up a video. And thank you, and we'll see you on the next one.